here's a way to look at this. We've said that the probability that y bar is between 64.6 and 65.4 is 0.95. Then we subtracted 65 from each of these quantities, and that didn't matter. So we said that y bar minus 65 is between negative 0.4 and 0.4 95% of the time. OK? But now what are we doing? Now we're going to divide each of these quantities by the square root of 4 over 100, which is 2 over 10, which is 0.2. What is 0.4 divided by 0.2? It's 2. What is negative 0.4 divided by 0.2? It's negative 0.2. Saying that y bar follows a normal distribution with mean mu and variance sigma squared over n is the same as saying that y bar minus this mean divided by the square root of this quantity falls with a negative 2 and 2. This is called the standard normal distribution. The standard normal distribution is just a normal distribution with mean 0 and variance 1. And this is now called a z-test. In order to do a z-test, we have to think about a sample that is coming randomly and independently from a population. Because of the central limit theorem, we have a reference distribution for y bar. And as we did when we started, we could just use y bar as a test statistic and use this as the reference distribution, and that's fine. However, the usual z-test, instead of y bar as a test statistic, uses y bar minus whatever null you're assuming divided by the square root of sigma squared over n. We're assuming we know sigma squared, and we really do know. And because all we're doing is subtracting something from each value in the normal distribution and dividing each value in the normal distribution by the same quantity, the reference distribution for this thing here turns out to be the standard normal. And this thing here is called the z-statistic. So what are the assumptions that underlie this test? We assume that our sample is independent. We assume that we have a random independent sample from the population. We assume that the central limit theorem is working here. The central limit theorem works if the sample size is big enough given the initial population distribution, as we can see by simulation. So we're assuming independence. We're assuming that the central limit theorem is working because the sample size is good enough for the particular population distribution. And we're assuming that we know sigma squared. And that's the one that's really ridiculous. That's the one that is not going to hold up when we try to use this method for a practical data analysis. So the next step then is to think about a version of this test that'll work when we don't know sigma squared.